We started back in 2014 as a little project, did a small token sale then, and have just kind of been writing code ever since. So like Swarm, IPFS, and a few other people, we build on Kademlia. We've talked about Kademlia a lot today. Does anyone need like a refresher on that? I can keep talking about it for hours. So unlike Swarm, we use vanilla Kademlia, no forwarding, unlike IPFS, which uses sloppy Kademlia, same as BitTorrent. But like Dev P2P, which Felix talked about earlier, we use it almost exclusively for routing. DHT storage in the past has not scaled very well. LimeWire and Gnutella didn't work super great because they use the DHT directly. So on top of Kademlia, we've built a simple system for storage contracts. That's really what storage is. One-to-one, peer-to-peer storage contract negotiation and arbitration. So we use pretty simple terms, renter and farmer. And on the network, you run a node. If you want to upload files, you're a renter. If you want to store files and get paid, you're a farmer. We use specialized nodes for these because really, there aren't very many people who want to do both things. If you have a lot of disk space, you don't tend to need a lot of storage. So you go on Kademlia, you build out your routing table, you get a bunch of peers, and we have a broadcast contract system. We actually use a publish-subscribe system called Quasar, which I'll go into in a second. You broadcast your desire to store a file. Some farmer who wants to get paid for that responds to you, and you enter a simple contract negotiation. Once you've transferred the shard or the file or whatever you want to store, we use a Merkle-based proof of custody, like Swarm does. I think you guys might have actually based Smash on some of our work. It's almost exactly the same thing. Yeah, well, that's one thing I've learned working on this is we're all rediscovering the same things over and over. There are, I think, 5 or 6 different competing implementations of Kademlia at this point, all made in the last 4 years. So you go on the network, you create a simple contract between renter and farmer. It says, I want to store 8 megabytes or whatever other amount of data. I'm willing to pay this much to store it for this time period. And so we use, like Swarm, a Merkle tree-based proof of custody, where the farmer can prove repeatedly over time to the renter that they still have the shard. Right? So the way this works is you have, what's the best way to explain this? You have basically a challenge salt, and you prepend it to the data and make a hash. You take the hash of that hash and make it the leaf of a Merkle tree. Do this repeatedly, you have a large set of challenges. You can issue a challenge to the farmer. If they still have the data, they can rebuild the leaf of the tree and send you back a proof, and then you know they still have the data. Each time you make a challenge, they have to prove that they have the data in order to receive payment. So it's an interactive proof of custody. Any questions at this point? Yes. So the renter needs to store the challenge salts. So in order to verify the proof, you need to store the salts so that you can issue them as part of the challenge. And you need to store the Merkle root of the audit response tree. Right. Yeah. Yep. Yep. And the consequence there is that you have a limited time span, and then after that you have to pull it back, regenerate more. But because hashing is really cheap, you could generate tens or hundreds of thousands of these and build a single tree and keep it out there for a very long time. Let's see. So that's really simple. It's a one-to-one storage contract that you can prove that the counterparty is behaving as intended. Either they're responding to your challenges correctly or you're issuing payment to them. Each party has guarantees from the other. But it doesn't solve things like performance or availability, really. If your farmer goes offline, you stop paying them, but how do you guarantee that they don't go offline? There's really no good solutions to that. So instead of just one-to-one storage contracts, you want to split up your file into a bunch of redundant chunks and spread them out on many farmers. So you have this kind of one-to-many relationship where one renter has many contracts with many farmers. And so for each file, you want to have multiple redundant copies. You want to use erasure coding so that even if a few drop off, you can rebuild them. And you want to have really high availability on your renter. You want to have it up all the time. You want to have 100% uptime if possible, and you want to be sure that you trust the renter. So we advocate that everybody run their own renting node, or pay someone that you trust to run it for you. Did you have a question? Oh, sorry. Let's see. So that's the basic architectures that we have. Specialized node types: renters and farmers. Farmers store data, renters consume it. Yeah, so we have some high-level convenience over the renters. So all file management is done via the renters. Like, the farmers don't even know what they store. They have encrypted chunks. So when you want to talk about hosting an entire file or hosting an entire library or data set, you do that from the renter level. So we have what we call a bridge that manages a pool of renters. It's a way to abstract away the complexities of the DHT and cryptocurrencies and provide a simple API. So the bridge node manages a set of renters. The renters procure contracts on the network, manage payments, manage contract negotiations, that kind of thing. And the bridge provides a RESTful API that gives information about contracts, information about files. All of the abstraction happens at the bridge level. Yes. So we use Kademlia. We use it for routing. So when you join the network, you contact the Bootstrap node, build out your routing table. When you want to store a file, or if you have space available that you'd like to sell, you broadcast a contract offer using a publish-subscribe system. And so anyone who sees that message that is interested in storing that file for you and being paid will respond, and you'll enter a negotiation process. Yes. It's the renter's responsibility. Generally speaking, in our system, if you want something to be available and performant, you need to manage it. That's why we have the renter and bridge model, is to solve that problem. Off-sourcing things to a distributed network is unpredictable and dangerous a lot of times, so we want to start at a more you control your own things level and then move that direction over time. Yes. So that's actually a little more of a complex question than it appears, because you have the core protocol layer with renters and farmers. You can run your own renting node. In that case, you'll have to manage the infrastructure for that node. You'll have to host that server or whatever. You'll have to keep it up. So if you already can do that, it's much cheaper than Amazon. The next layer of abstraction is the bridge. If you want to use someone else's bridge as a service, you can do that. We'll sell you that service, and we charge about half of what Amazon does. And in that case, we'll be managing the bridge infrastructure. We'll be providing access. There are tons of client libraries to access files on the network via a bridge. The advantage of the bridge model is that clients can be naive of the protocol and network. When a bridge is helping you get a file, you don't have to understand a DHT. Your client doesn't participate in the DHT at all. And that makes it a lot easier to develop with, because it behaves similar to S3 or another object store. So a farmer can expect to earn, I think, a quarter to a fifth of what Amazon would earn. And it's a little complex because you have to talk about redundancy for the file and yes. So if you're a renter on the network, if you're using the base protocol, it's your responsibility to know where your files are. You're managing the state of those. You have contracts with the farmers that store them. If you lose their contact information or it changes, you can use Kademlia to find them again. But you're responsible for knowing that. If you're using the bridge abstraction, then the bridge stores that information and can provide it to clients. And one of the reasons that abstraction is useful is in Kademlia, you're going to make a many-step lookup. And you might make thousands of lookups, which are each several steps, in order to find an entire file composed of many chunks. But with the bridge model, it's always a one-step lookup for the entire file. So it's a pretty significant performance increase. You have to trust somebody. We're suggesting you trust yourself. If you're not actively on the network managing your own file, how do you expect it to still exist? What's that? Run your own bridge. It's all free software. JavaScript, Node.js. Yes, we can do that. So again, the renter is responsible for making all decisions about how the file is distributed across the network. If the renter would like it to be available to many people, they can make the retrieval information available. They can split it up across dozens of nodes instead of a few. They can distribute it however they think is best. One of the kind of interesting problems in this space is how to stripe data across the network effectively to meet certain goals. If you're trying to make a video available to dozens of people, you're going to use a different distribution of shards on different farmers than if you just want to archive something for a few months. And the renter is responsible for making all of those decisions. So it's a simple automated process right now. Is basically there's a contract data structure, and you fill in parts of it and sign it and send that as an offer. And then your counterparty, if they don't agree, will change parts of it, sign the new version, and send it back. And you repeat until you find something you agree on. In the future, we can implement a bunch of different negotiation strategies, and that's going to be a long-term area of research. Right now, the negotiation process is far cheaper than the actual broadcasting of offers. Once you've got someone who wants to transact with you, that's all very quick because it's one-to-one and it doesn't use the DHT at all. I guess I could talk a little more about our publish-subscribe system, if people are interested in that. I don't know how much time I have. Or do we have an eraser? This one. Ah, it's right next to me. I thought that was a mouse. All right, so is anyone here familiar with Bloom filters? Yeah? Great. I'm going to talk about them a little anyways. But we use a system called Quasar for publish-subscribe. It was invented by some researchers at Microsoft a few years back. It's a peer-to-peer topic-based publish-subscribe system. So Quasar uses what's called attenuated Bloom filters. And the way a Bloom filter typically works is you have a subject that you're interested in, let's say cat, and you're going to hash it into a bit string. I'm going to simplify this a little bit. Anyone who actually knows Bloom filters, it's a little more complicated. But you hash your topic that you're interested in into a bit string. Any other topics that you're interested in, like dog, and you take those bit strings and you combine them. So in this case, we're going to use logical OR because it's really simple. And that is your filter. Anytime you find an incoming message, let's say the incoming message is rabbit, you're going to hash it. And then see if that bit string is in your Bloom filter. So the interesting thing about Bloom filters is that there are false positives, but never false negatives. Logical AND, in this case, for the simplified version. So in this case, we can say logical AND is 111011. So this string is in our Bloom filter because every 1 bit has a corresponding 1 bit in our filter. So the interesting thing about Bloom filters is they have false positives. So in this case, rabbit is not actually a topic we're interested in, but it is in our Bloom filter. But there are never false negatives. So if, for example, rabbit were 00101, sorry, where did I go here? Man, it's been too long since I looked at this. So you do logical and then you compare it to your own filter. So in this case, there's a bit in the bit string that's not in our filter. So we can tell that rabbit is not in our filter. You get a negative. So any questions about Bloom filters? Perfect. All right. So in Quasar, you use attenuated Bloom filters to predict what your neighbors want and their neighbors. So in this case, let's see, you have your Bloom filter, and then you keep, for each K bucket in your routing table, you keep another Bloom filter. So this is my closest neighbors, and then you keep more and more Bloom filters. So your filter is your interest. Your neighbor's filter is your 3 nearest neighbors' interests, and as one filter, and then the next closest neighbors, and on down the routing table. So in this way, you get not only an idea of what you're interested in, but also which direction to rebroadcast messages to people who might be interested in them. So whenever you get a message in, you hash the topic, compare it to your filter, and then compare it to your neighbor's filters down the table, and forward it to the neighbors that you think would be interested in that topic. In this way, messages kind of propagate through the network until they find someone who's interested in them, or until they find a rumor of someone who's interested in them, and then from that point on, they propagate towards the nodes interested in them, which is a little annoying. And gossipy algorithms are not always the best choice for an incentivized network, but it's working well so far, and we'll upgrade it if we feel like it needs it in the future. Any questions about this? Yes, Felix. So for each bucket in your routing table, for each relative key space, you keep a Bloom filter that describes what the peers you know of in that neighborhood want. It's the distance metric as usual in Kademlia. And so when you exchange interests, when you exchange topics, you actually exchange your entire filter list. So I exchange my filter with my 3 nearest neighbors. They give me their filters, but they also give me their view of everybody else. That is problematic. In order to, so like Bloom filters break down when there are a lot of topics. So we have a very narrow topic set right now. I believe we only have something like 16 topics. No, it doesn't assume correlation. What it does is so the goal is to get the message into a neighborhood where at least one person is interested in it. And then once the message is in that neighborhood, it propagates to the nodes that are interested in it. Because the nodes who are in that neighborhood will have a better idea of which nodes in that neighborhood want the message. So right now what we use this to do is to broadcast contract offers. And so we have a few... Not all files are created equal, and people don't want the same performance for each file. So we use the topics to describe things about the proposed contract, like how big the shard is, how long it's going to be stored, what kind of bandwidth you need. And you take pretty simple codes for each of those and combine them into a bit string, and that's your topic. I think right now we have three aspects with 3 divisions each, so there's 27 different topics, which is more than small enough to prevent Bloom filters from getting overcrowded. So when you're broadcasting a contract offer, you describe it as large file, long-term, low bandwidth. Create a topic out of that, hash it, and broadcast the message. So generally what we like to do is extend Kademlia, so there are now protocol messages in storage for notifying your peers that your filter has changed. And each time you do that, you also receive in return their filters. And so every time that you're changing your topics or every time you hear about someone else's, updated topics, you adjust your bloom filters. Right. So it's gossipy with your neighbors. So we have registered with our bridge server that we run. We have about 25,000 users. Daily average users is much lower than that, but we have, I think, managed by our bridge server right now about 3 petabytes of data. A lot of it's, test data that was uploaded as part of our beta test. We know of at least 3 other people running major bridge servers. We don't know exactly what they're doing with them, though. Probably not. We're a little small scale for them right now. You obviously can't tell exactly, but we think the network has about 7 petabytes of capacity and about 15,000 nodes. Well, we've been doing this a little longer than you guys. Well, we're working on that. Is Swarm still in controlled testnet, or is it out in the wild now? So there's some downsides to our model, which I think Victor's given us some flack about in Gitter, is because you use the renter and bridges, you don't have strict content addressability. You can't use the hash of a file to go out into the network and find it without anyone facilitating you. The trade-off for that is that lookups are always one extra hop, in that you know that there is a bridge or a renter that has the information you want. And that makes lookups much more consistent and reduces time to first byte by quite a bit, usually. So yeah, in terms of Swarm, you get caching by default by using forwarding kademlia. In IPFS, you get caching by default using sloppy kademlia. With our system, you need to take care of it yourself. Take care of your own caching, take care of your own scaling. We want to look at using something like Swarm as a caching layer in the future, but it remains to be seen how exactly we'd do that.